Hello, this is Mrs. Taylor, and I'm going to walk you through how you can go from working with Riemann sums into definite integrals. So far in class, we've been approximating area by calculating a sum of the areas of rectangles or trapezoids associated with the curve. And we agree that if there are more rectangles or trapezoids, the approximation would be more accurate. So if we focus on the number of rectangles approaching infinity, we begin to look at limits. And so the idea is the rectangles get smaller and smaller in width, they reflect the behavior of the curve more closely. And of course, when we want a large number of something, we're talking about it approaching infinity. And so first, in order to understand, we have to know about Riemann sums and sigma notation. And so here are three examples of sigma notation. Sigma notation just indicates a sum, and you have your bounds. 2 to 5 here would mean that you would add your values, the second, third, fourth, and fifth. And so your 2 would go in for your variable, and you would evaluate, and then the next whole number would be 3, plug it in, evaluate all the way to 5, and then the sigma part tells you to add all of those together. And so the same is true for this situation where your m, your variable, is raised to the second power. You raise each whole number from 3 to 7 to the second power and add all those together, and that gives you the sum. And so in general, what we have is our sigma notation. Sometimes you'll see your indexes written here instead of above and below, but it's from k to n for whatever your formula is for the sum, and then you would plug in each whole number from k to n and then add those together. And so to understand Riemann sums in particular, not just sums or sigma notation, we need to know about George Riemann, and a Riemann sum is the sum of the values of a function taken at a point in each subinterval multiplied by the width of that subinterval. So what we need to understand is that we've worked with LRAM, RRAM, and MRAM, and they are particular types of Riemann sums. So there are other Riemann sums out there. So to understand the notation, let's put it in the context of our RAM, our rectangular approximation method. So again, don't forget that Riemann sums are not just strictly for area under a curve. That's just where we use it in calculus. And so in this setup of a Riemann sum, we have sigma notation, and our k value starts at 1 to represent your first rectangle, and n represents the number of rectangles. And then the f of x sub k represents your height, because remember your height of your rectangle is your y value. And then delta x represents the width of your base. And remember that delta x is just your right bound minus your left bound divided by the number of rectangles. And so that's how you would find the width of each rectangle, and that would be your value for delta x, and then your y values would change according to where you were in your interval. Alright, so now let's look at what happens when we want infinite rectangles. So we have our Riemann sum that represents our rectangular approximation method, and what we're going to do is we're just going to write the limit as n approaches infinity out front. So what that tells me is that n, which represents the number of rectangles, is going to approach infinity, which means we're going to approach infinite rectangles. And so we're trying to get as close to the exact area under the curve as possible. And so when we put that limit out front, that's when it becomes a calculus situation, and that's where we start moving into integration. So instead of sigma notation, mathematicians developed integral notation. And it looks like this. And so the idea is, instead of the sigma symbol, we have this integral symbol, which looks like a stretched out S. And so both indicate a sum, it's just an integration, it's the limit of a sum. And so our n, our number of rectangles, is linked to the b value on the definite integral. Our k, our initial, is linked to the a, our lower bound of our definite integral. And then our f of x stays f of x. And delta x becomes dx, which makes sense because when we work with derivatives, remember the delta x in slope, delta y over delta x, was kind of linked to dx when we took the derivative. So we had delta y over delta x, dy over dx, and those are differentials. So they all mean the change in x or whatever the variable is. And so really, it's exactly what we've been doing with the sums, the sigma notation. It's just different notation than we originally had worked with. So just a little information about what to say when we are talking about this notation. This statement here, when written this way in integral notation, the way we read this is we say the integral, the symbol, from a to b of f of x with respect to x. So similar to derivative language. And a and b are referred to as your limits of integration. F, your function, is referred to as the integrand. Just like when we have radicals, we have a radicand. It's an integrand. It's the function you're taking the integral of. And d of x is the differential x, or change in x, or in this case, when you want to refer to the entire integral with respect to x. Alright, so let's put this in a context. In this particular situation, we have the interval -1 to 3, and it's partitioned into n subintervals of equal length, delta x. So that would be the width of our rectangles, and n represents the number of rectangles. And so we're going to let m sub k denote a midpoint of each subinterval, and we want to express the limit as an integral. So the idea is we're going from -1 to 3, and we want to find the area under the curve, and we're using midpoint. And so our x values would be the midpoint of each subinterval. So the idea is when we have this limit as x approaches infinity, it should read n approaches infinity. Let me correct that. Much better. So the limit as n approaches infinity indicates to me that instead of just a sum, this is going to be an integral. And we have our usual notation here. Our first index is 1, and then n would represent the number of the rectangles, but in this case we want infinite number of rectangles, so that's why it's indicated as n and not a number. And then here we have our f of x sub k, and then delta x. And so my integral would look like this. My limits of integration, -1 to 3, that's our interval we're integrating on. And the function f of x would be simply what's written here, but instead of m sub k, it would just have x. And then instead of delta x, you would have dx. So it's a really easy transition from sigma notation to integral notation. So here's the bottom line of all this. You need to recognize the definite integral as the area under the curve. Anytime you see definite integrals, you're analyzing the area under the curve in some way. So sometimes it'll be in the context of a word problem, sometimes it'll just be evaluate the definite integral. And according to the context, we'll determine how you set up your definite integral, how you interpret it. But for purposes of right now, we're just thinking of it as area under the curve. So let's say we're given this problem. Evaluate the integral, and it's the definite integral from -2 to 2 of the square root of 4 minus x squared with respect to x. And so one thing that could help us with this, because we haven't been told how to do this algebraically, but the one thing we can do is graph the function, and maybe it'll help us. So if I graph this function, and you may already recognize it, but if I graphed it, what I would see is that this is the function for a semicircle. And semicircle is just half a circle. And if we are interpreting this definite integral as the area under the curve, then really all I'm finding is the area of this semicircle. And it intersects the x-axis at 2 and negative 2. And that is my upper and lower limit of integration. And that's also helpful because that tells me the radius of this semicircle is 2. And so instead of doing some type of algebraic method here, if I recognize this as area under a curve, then I can just think of the area formula for a semicircle, plug in my radius, and evaluate. And so that's what I'm going to do in this case. So it would look like this. Area of a circle is pi r squared, but this is half a circle, so it would be 1/2 pi r squared. We established that our radius is 2 because that's where our curve intersects the x-axis and the y-axis. And so if the radius is 2, I would just plug it into the area for a semicircle, 1/2 pi times 2 squared. 2 squared is 4, 4 times 1/2 is 2, and so my area is 2 pi. And so since the area between the curve and the x-axis is 2 pi, then this definite integral equals 2 pi. And that's all I have to do. And so that's how I would go from a Riemann sum to a definite integral.